In the intricate world of computing, operating systems, or OS, reign supreme, managing everything from hardware resources to user programs. But how do user programs, confined to their own memory spaces, interact with the all-powerful OS kernel? Well, this is where system calls come in, acting as the crucial bridge between user space and kernel space. Imagine a system call as a carefully guarded doorway into the OS kernel's domain. When a user program needs to perform a privileged action, like reading from a file or sending data over a network, it requests the operating system's help via a system call. This request triggers a switch from user mode to kernel mode, where the OS carefully verifies and executes the requested operation. This controlled access mechanism ensures system stability and security, preventing rogue programs from wreaking havoc on shared resources. System calls provide a well-defined and secure interface, abstracting the complexities of the underlying hardware and providing a consistent programming experience across different systems. In essence, system calls empower user programs with the ability to leverage the full potential of the operating system while maintaining a clear separation of concerns and ensuring overall system integrity. System calls are as diverse as the tasks an operating system performs. To better understand their roles, we can categorize them based on their functionalities. 5 common categories include process control, file management, device management, information maintenance, and communication. Process control system calls manage the life cycle of a program, from its creation to its termination. Examples include fork, which creates a new process, and exit, which terminates the calling process. File management system calls handle interactions with the file system. These include open, read, write, and close, enabling programs to create, access, modify, and delete files. Device management system calls provide a way for programs to interact with I/O devices like printers, scanners, and network interfaces. Examples include IOCTL, which controls device-specific operations, and read and write, which handle data transfer. Information maintenance system calls provide access to system information like the current time, system uptime, and available memory. Examples include time and getPID. Finally, communication system calls enable inter-process communication, allowing processes to exchange data and synchronize their actions. Process control system calls form the backbone of modern multitasking operating systems. These calls empower the OS to manage the creation, execution, and termination of processes, ensuring that multiple programs can run concurrently without interfering with each other. One of the most fundamental process control system calls is fork. When a program calls fork, the operating system creates a near-identical copy of the calling process, known as the child process. Both parent and child processes continue execution from the point after the fork call, each with its own memory space and resources. This powerful mechanism enables parallel processing, where tasks can be divided and conquered by multiple processes, significantly enhancing system performance. Another crucial process control system call is exec. This call allows a process to replace its current program code with a new one, essentially transforming itself into a different program. This is particularly useful when a program needs to execute another program as part of its functionality. Finally, the exit system call allows a process to gracefully terminate itself, returning control to the operating system. The OS then reclaims any resources held by the process, ensuring efficient resource utilization. Section 4. Managing data, file and device system calls. The lifeblood of any computing system is data, and managing that data efficiently is paramount. File and device system calls provide the essential tools for programs to interact with this data, whether it's stored on a hard drive, SSD, or accessed through a peripheral device. The foundation of file management lies in system calls like open, read, write, and close. Open establishes a connection to a file, returning a file descriptor, a unique identifier used for subsequent operations. Read and write facilitate the transfer of data between the file and the program's memory space, enabling data persistence and retrieval. Finally, close severs the connection to the file, releasing the associated resources. Beyond file manipulation, device management system calls extend the reach of programs to the vast array of peripherals connected to a computer. These system calls abstract the complexities of device-specific communication protocols, providing a consistent interface for interacting with devices. For instance, a program can use the IOCTL system call to control the behavior of a device, such as setting the baud rate of a serial port or adjusting the volume of a sound card. Similarly, read and write can be used to send and receive data from devices, enabling communication with external sensors, actuators, and other peripherals. Section 5, Beyond the Basics, Information and Communication.